Okay, hello and welcome to today's lecture. We are already in week 9. Today I'm here with David, and the main topics for today are files and data structures. But first, as always, we have a quick look into the organizational matters. So as I mentioned, we are already in week 9, and today we hand out the weekly exercises 9 with deadline similar as or the same as for A4 in 2.5 weeks on 21st. Sorry, not 2.5 weeks.
No, it's the deadline is for assignment 4 already. So
yes.
So these are the first one who belong to assignment 4. And the deadline is the 21st of January.
Of January. So yeah, more than 2.5 weeks. So it's more than 1 month you have time for those exercises and A4. And as usually the reminder that you have to pass at least 50% of the weekly exercises to avoid point deductions for the assignment. So yeah, and this is the first exercises for or according to A4, and next week in our last regular lecture you get the next and last exercises for A4. And then in 2 weeks, we have our last lecture, which is the Christmas special then.
Yeah.
Okay. As recap from last lecture, which is already 2 weeks ago, we have prepared a few quizzes. And the first one is about, this code snippet, and you have to check what the output is. You have a few options here. So we have a main function and a create array function where we have a malloc inside. And afterwards, in the main function, we access the array at position 2, set the value to 20, and print the value then. Afterwards, we free the array, and the question is what the output is, whether it's 20, whether it's undefined behavior, a segmentation fault, or a compiler error. So already 30 of you have joined. Let's wait a few more seconds. Maybe until we reach 40. Yeah. Okay, yeah, most of you got it right. That we get a segmentation fault here. So what's the problem? We pass the integer pointer array to this function here, and then we call malloc and store the pointer that we get in heap pointer, in this pointer here, but the function does not return anything, and so in the main function we do not override our array integer pointer, meaning that there is still null in it, and when we access it here, when we want to access it at index 2, we get an segmentation fault in this case. Next quiz is similar code, a bit different, and now the question is what is missing here, which code is missing here, that in the end 20 is printed. We have a few options here. whether it's int, it's an integer pointer, it's an integer pointer, or int with this address of operator. Yeah, already reached 40 participants again, so we can check. And again, most of you got it right. So it's the int pointer in this case, because now we pass into this create array function the value of the address of array. So the address of our integer pointer, where the pointer null is stored, the address of this integer variable or integer pointer variable. And so we can take it as an int pointer. If we dereference it, then we can write into this address. And there we store then what we get from malloc. And afterwards, yeah, we do null checks and print 20 in the end. Great. And third and final quiz is related to what have been shown in the practicals regarding realloc. So what are the potential issues with this code? Again, a few options are available. So at the beginning, we have a malloc with 3 times the size of int. We store this pointer in grades. We check for null. We set the 3 values. And then we do a realloc. We want to resize it to 5 times the size of int. Then we check whether grades is null, and afterwards we access the 3rd and 4th index, and afterwards in the end we free the grades pointer or grades memory. Okay, yeah, the memory leak if realloc fails is the potential issue here, which most of you again spotted right.
One comment from my side.
Yeah.
I would also check missing typecasts, because you could write typecasts there.
Sure.
But it's not really an issue.
Correct. Yeah. So
yeah.
It's not really an issue, correct? But we could have stated that it's missing at least here. Yeah, correct. Yeah, but now let's have a look what the problem really is in detail again. So this was the code that we have shown in the quiz, and yeah, until here, we just allocated memory on the heap, so 3 times the int, and then we stored values in it, and we have the pointer in our grades variable, and after realloc, if it fails, the grades pointer is set to null, as we store the result of realloc in grades. And if this is null, we want to quit our program with return 1, but now the problem is that we lost the reference to our first allocated memory on the heap, which has not been freed by realloc, and this would cause into a memory leak. So the solution for this could be to store it in a temporary value or variable to get this new value, new pointer here in temp. And if this is null, only temp points to null, but the old grades pointer is still stored in grades, and then we can also free it here. And this would be the correct solution then to avoid memory leaks in this case. Great.
Okay, I think we can now make jump back to constants, which we already discussed.
Yes.
I think in week 3 or
yes,
week
it
4,
was
like week 3.
Week 3, yeah.
And we had to add something there now.
Yes.
Because we discussed define, and define is a cool way to kind of, for example, define or give a value a name and then use this name instead of the value for hard-coded values, for example, pi. But what you also can do is, very similarly, is to write it like this with const. So const means that we create a variable who cannot be changed, so constant basically. And the difference to define is that const really is a variable, while define is just like it is substituted during compile time from the compiler. So const really takes memory in your program because it is like a variable, while the define is just a replacement of the name and the value. And the advantage of const is that you can use types. In this case, we have an integer. Of course, you can also use other types, and you can calculate with these types.
Yes. So with define, we do not have this type check because it's, as David just said, just similar to a find and replace by the preprocessor. So the preprocessor does just a find and replace for you everywhere. You, in this example, where you have p, it gets replaced by this value afterwards, and there is no check for the data type.
Yeah.
But const for const it is, and yeah, as I said, it is a variable that is made constant because it cannot be changed anymore.
Yep. And the cool thing now is we always say to you that you should not declare any variable globally, so outside of functions. With constants, you're allowed. Yeah, constants you can write globally, similar to defines, write it on top of your program, and then you can use it the whole program. It's a very nice way. It's an alternative way to use constants like define. But I think we already have here and there some constant values shown.
Yeah.
Just for completeness, we wanted to add it here.
Yes. Okay, so why would we use now constants? As David just mentioned, you can now use them, for example, as global variables, so to speak, but it also could improve the readability of your code because you can give them meaningful names, as in our example before, p or max value for an array, for example, and so on. And you can maintain your program easier because you just have to change the value at one position to then, have it changed everywhere in your program where you use these constants. Okay.
Okay, yeah. Second small topic we wanted to add are enums. And enums are a nice way. It's, again, pretty related to the constants. So imagine we want to represent all days of the week, and you have to declare 7 times, okay, Monday, Tuesday, Wednesday, Thursday, and so on, because we want to calculate with that or want to show it in any way. And there is one improvement to writing it like this.
Yeah, so we could do it like this, but there is a better solution because now we could use enums, and enums work like this, that we say enum followed by, let's say a list of names that we can define. For example, Monday, Tuesday, Wednesday, and so on. And afterwards, in our program, we can use those names that we defined here in our enum as if they would have been constants, for example.
Yeah.
And now let's have a look which values do they have. So in this case, if we just write enum followed by those names, if we access those names, they are basically just integer values starting with 0. So as you can see here, Monday is 0, Tuesday is 1, Wednesday is 2, and so on, in increasing ascending order in this case. So if we then print Tuesday, it's just the value 1. So now we have 7 possible values that we can now use. In this case, it's the weekdays, making sense that it's just those 7 values. But we could also specify the values behind those names. So we can say that we do not want to start with 0, but with, for example, 10. Then Monday would be 10, Tuesday would be 11, and so on. And we could also mix this definition or setting of the values, because we can say Monday is 10, Tuesday is 2, and so on. So they have different values now. And if we stop defining them, it's just, an increasement or increasing the last variable always again by 1. So Saturday and Sunday would then be 45 and 46 and so on. So what can we do now with those enums? We can use it, as we just have shown, without a tag, and we could also use them with a tag. So we can say enum weekdays, meaning that we call this list of names weekdays to give them a meaning. And what we also could do is to type def this new data type, so to speak. So we can say type def enum weekdays, then followed by the list of names we want to define. And in the end, as we know this from type def, we can define a new name for this new data type. And afterwards, we can use the weekdays as a data type, and we can also define variables from this data type weekdays. So we can say weekdays current day is Thursday. If we then print Thursday, it prints again the value behind Thursday, which is in this case 0, 1, 2, 3.
And this is a very good example what enum is all about, because under the hood, weekdays is just an integer. Thursday or Tuesday is just a number. In this case, Thursday is 4. So the program doesn't really change, but it's a lot easier for us to read the code, because the current day is now Thursday, is for us human being a lot easier than current day is 4.
Yeah, correct. So for the user of our program, it doesn't really matter whether we use enums or not, but for us programmers, it's much easier than to read our code and to structure our code. And as you mentioned, it's just an integer behind each name. We can also now work with those integers. We can calculate with them. For example, we can say we define a variable today from data type weekdays, and we define it with Thursday, meaning 3 in this case. And then we can say we want another variable tomorrow that is calculated with our or by our function next day, where we pass the variable today. So let's have a look. This next day function takes a weekdays variable, car day in this case, or current day, and it also returns a weekdays value. And what we do inside here is just increasing the value that we get passed here. So in the end, we would return, in this case, 4. So if we then print in the main function the tomorrow variable, we get the output 4. But we have to mention here that if we, let's say, run out of the range of our predefined names, meaning that if we define Sunday here and we would call next day, it would not go from 6 to 7, from 6 to 0 to Monday. Mm-hmm. It would go from 6 to 7, meaning that we do not stay automatically within our range. So we could solve this problem by just using the modulo operator to stay within our range of 7 weekdays. So in this case, if we pass Sunday here with the value 6, then we add 1 to the value would be 7, modulo 7 would then be 0 in this case. And now we can ensure that after Sunday, which is 6, we get back to Monday with the value 0. So we have to do this manually. Otherwise, we could get values that are outside of our enum range. Yeah, and there's even nicer solution for this, because now we have to, we have a hard-coded value 7 here. Yeah, for weekdays, I think it will always be 7, but
hopefully, yeah.
If we have another use case where we sometimes maybe want to add further names afterwards, we would have to extend this or increase this value, right? And one solution for this would be to add an 8th name for this. In this case, I call it weekday count. And since we start with 0 for Monday, this weekday count would get the value 7. And now I use this last value in my enum for the modulo operation. And if we then would extend this enum range by further names, yeah, it would then be automatically be updated here as well.
It's a nice solution because you always have the count inside the last element.
Yes.
That's interesting.
So the counter is, within our range, the last element. But it's, the same. It's just another element, right?
Yeah.
But it gets always the value, the last value, which is actually the number of all the values before. Okay, so the advantages of enums in C are that you can now organize values that belong together, as in our previous examples, the weekdays, and you have those numerical constants together in one place with meaningful names. So it really improves the readability in this case, because now we can, if we see it's Monday, we know it's 0. If we see the code or in the code Tuesday, we do not always have to calculate what is Tuesday, which number has Tuesday. We just work with the name instead of the number behind it. And it enhances the maintainability, because now if I want to change something, I just have to change my enum, for example, to add or remove values.
And one possible application would be, so as you said, there are related constants. So I assume in your program you would have different exit codes of your program. They are somehow related, so an enum would be a good idea to use here.
Mm-hmm.
Okay, I think there were two very, very easy topics in the beginning.
Yes.
So I think we can a bit improve and let's make it a bit more difficult.
Yeah. Now we come to the main or larger topics for today. The first one is file I/O, meaning that we now want to work with files. So we want to open files, read data from files, or even write data to files to store something calculated in our program in files, for example.
And that's very, very important, because when you think about any program, they are usually working with files. They're not always working with user input and user output, and not only in the terminal, they're working with files. So I think that's very important.
Mm-hmm.
So when we talk about general input and output of our program, we always say that there is this standard input from the keyboard, from the user to our program, and then we say there is this standard output from the program to, let's say, the terminal. Yeah. And there is another one, I think we didn't mention until now.
I don't think so. I don't think so, yeah.
There is a second output possibility from your program, which is called standard error. This is just an alternative way to print to your terminal. In many IDEs, it's just printed in another color, mostly I think in red. Yeah. And it's meant to be used with, I don't know, if an error occurs. We in ISP do not allow printing on standard error because we want to have all the output on standard out, but there is this possibility. But so this is streams, which means standard input streams, standard output streams. This can be text streams, or it can also be binary streams. So text usually is user input, binary, I don't write binary input. So there is another possibility to interact with programs with binary.
Yeah, so what we have seen until now is, for example, the scanf and the printf function, which could basically also be written with an fscanf and an fprintf, where we have to pass the standard input and standard output as first argument. And in this case,
what could this
F
be?
mean? Yeah. So
we're talking about files
today. So F in this case stands for file. So now we can scan and print, so scan from files and print to files. And in this case, our file is just the output and the input stream.
So the standard input and standard output is just a specialization of a file, because they just said, it doesn't matter if it's a real file or it's just a keyboard. It's something that goes into my program. So let's say stdin is just a file.
Yeah, and now we can change the standard in or the standard out with files. And then we can write to files or read from files, and we can do this with fscanf and fprintf. But now let's have a look what the difference is between text files and binary files. So we have two examples here. The first one on the left side is a text file, which can be opened with a text editor, and then we human can read the text inside. So we can read it and understand it. But if we check binary files, which are, for example, the executables that you produce when you compile your program, or any executable file, or, for example...
In this case, it's a Java file. But of course, also with your executable files. Maybe you already tried it once. I tried it back in the day when I wanted to see what this executable file looks like, and I was confused to see something like this. The computer can interpret it.
Yes. So the reason is that the values inside are not really the ASCII values we have in our text files, but it's just binary values. And they have a specific meaning for the programs that uses those files. But for us humans, it's not really readable what's inside, because it's binary values and not text. So this is basically the difference between text files and binary files.
But it does not really matter to us. Of course, we have to interpret the content differently. So there's a difference if I want to read a text file or a binary file when I extract the content from the file. But general working with opening files and all what we will discuss now in the next few slides is similar for binary files and text files.
Yes. You just mentioned opening files. How can we now open a file from our hard disk, for example, when we are in our program? We can use fopen. Fopen is a function that is provided that we can use, and as the name suggests, it opens a file that is stored somewhere, for example, on my hard disk. And I can pass two arguments to this fopen function. The first one is the path name, where on my hard disk is the file stored. I have to pass the path. And the second argument is the mode in which I want to open the file. Is it, for example, to read, Is it to write? So do I want to read something? Do I want to write something into the file? Is it a text file or is it a binary file? And I can specify this in this second argument. And the pointer that we get back from this function is a pointer to the file that is located on the hard disk, for example. If this fails for some reason, because the file does not exist or I do not have permission to open the file, then I get a null pointer back, and so I can do a null check whether the fopen worked or not. After doing something with the file, so for example, reading from it, writing into it, I also have to close the file in the end. And I can do this with fclose. This function closes the before opened file.
It's pretty similar than working on the heap with malloc and then free. So you have to open a file and then you have to close the file. So the file is not closed as soon as the function is over. You have to manually close it again. So similar to malloc and free.
Yes. Okay. So let's have a look into the different modes that we can use when opening a file. So the first is just reading the file. So we have to pass R as mode. Then we open the file to read. If we pass W, this would mean that we want to write something into the file. And it also overwrites an existing file. So if there is already a file at this path and I open it with W, then the existing file would get completely overwritten. A is used if I want to open the file for writing again, but in this case it's not overwritten, but the content I'm writing into is then appended to the content that is already in the file. So if I do not want to overwrite it, but just append some data into the file, then I use A instead of W. Then there are the modes R plus and W plus for opening an existing file to read and write. And if I use W plus, it's creating a new file to read and write. So again, this overwriting if it already exists. And B would be the mode for opening the file as binary. So now we have to distinguish between whether we want to work with a text file or a binary file, and we can do this with this mode here. When I use B, then I say I want to use it and open it as a binary file. We now have 3 examples down here. So the first one is the fopen with a path to the folder temp with the file name myfile.txt, and I use the mode R, meaning that I open this file that is already existing here, and I want to that already exists here, and I want to read it. Second example is that I want to open another file. As you can see, in this case, it doesn't have to always have an extension. So this one does not have an extension in this case. And in this case, I want to open the file or I want to create it. If it does not exist, then I want to open it for writing, and I want to open it as binary. So as you can see, I can also combine different modes, as in this case, the W and the B. And in the third example, we want to open another file where we specify the mode R+, meaning that I want to open the existing file here for reading and writing. So those are 3 examples now how we can open files in different modes.
What's missing here, of course, is that we always have to check if fopen worked.
Yeah.
Because if it does not work, maybe the path is wrong, then we have to, of course, react to that because we cannot read from that. So we always, again, similar to malloc, check if the return value of fopen is null. If it's null, then it didn't work. there's a problem with the path, there's a problem with the permissions, whatever.
Yeah.
And then we have to react to this special case.
Because if we do not do this null check, then, for example, if we go further, as we can see on the next slide then, and if we want to read actually, perform a reading action on the file that has not been opened, we are working with the null pointer, which then causes to a problem. Yeah. So yeah, do the null checks immediately after fopen, similar as with malloc, calloc, and so on.
Okay. How can we read from a file?
So now we have opened a file, and to read from a file, we could use different functions. The first one is fgetC. So yeah, similar to getC that we have already seen. So fgetC takes as a parameter here the file pointer from a file that we've just opened before, and it reads one character from the file. So with this function, I could read character by character from the opened file.
What we usually have used is fgets already.
Yes.
And we already had this f inside.
Yes.
Why?
Yeah, because we already used the file, so to say, standard input stream.
Yeah, but now we can use it with files too.
Yes, but it works similar. So the next function is fgetS, and in this case, we have to pass here a buffer, a character pointer, an integer, and again a file pointer. And this function reads n-1 characters, so n-1 that I pass here n-1 characters from the opened file into the buffer that I provide here. And fgetS stops immediately at EOF.
We'll come to that next slide.
Yes, at EOF or at \n, so at new line. What EOF means, we'll see on next slide. And the third function is fread, where we have to pass again a buffer, a size, n, and a file pointer. And this fread reads n items with the size, so n items with the size from the passed file into my buffer. The difference here is, that it does not stop at \0 or n, as compared to example for fgetS.
So there's a risk to write further than I actually would want.
Yes.
But it gives me a bit more flexibility to not only read until the new line, but read multiple lines, for example.
Yes. So what is EOF? We just mentioned. EOF is a special character, and it just stands for end of file. And this for sure makes sense, because if we want to read from a file and we reach the end of a file, we do not want to read further because we already reached the end. So it makes sense that the function stops reading here, right?
Yeah. So EOF is basically the last character in every file, which is this EOF special character.
Okay. And we have here an example where we first open a file called example.txt without any absolute path, so it's just within the directory we are also starting our program, for example. Example.txt with the mode R, meaning that we want to open it for reading. And afterwards, we check for null, so whether this opening of this file worked. If it worked, then we do the following. We have here a while loop where we say character, or short version for character, is fgetC, and we pass our file pointer into fgetC. And we do this as long as we do not get the end of file. So as long as this is unequal to end of file, we do the following. We do put char of this previously read character. So we read a character, put it into the standard out stream.
The put char is basically another version of printf, just puts it to the standard out.
Yes. And we do it until we reach the end of file. And in the end, we close the file with fclose. Yeah, this is the first example how we could read a text file character by character and doing something with it. In this case, just printing each character on the standard out stream. Okay, the next thing would be writing into a file, which is quite similar, but now the other way around. So instead of reading, we are writing, and we have similar functions. So the first one is fputc. So you can write a character to the file. We have to pass the character and the file pointer, and then this character is written into the file. We can do again an fputs. So we want to write a string, a whole string that we pass here as first argument, and again the file pointer as second argument. Now we write the string s to the file. And the third function is fwrite, which is kind of the opposite to fread. Now we provide a buffer here, again a size n and a file pointer, and this fwrite means that we want to write n items with the size now from the buffer to the file. Yeah, and this function returns us the number of written objects, meaning that how many items were actually written.
So when we work with reading and writing to files, there's one problem. When we write the code, or when the code is executed, we cannot see the text file itself. We don't know exactly what's the content there, which makes it a bit hard for us to identify where in this text file we are currently are. And luckily there are again some functions that help us to kind of orientate where we are in these files. One of them is ftell. Ftell, really good name, I would say, returns so it tells me the current position in the file. Basically, it says you are at the 5th character, 10th character, whatever. And when you enter, so when you write something, it will be the 6th character. Or when you read something, it will be the 6th character, whatever. So ftell gives me the current position, like a cursor in Word, where you have a current position in your text file, and ftell says where you are currently. Sometimes you get lost in your current position. I don't know where you are. There is a rewind function which sets the current position just to the beginning, because you can say, oh, I don't know where I am, or I just want to start from the beginning again. Let me go back to the first position again, and I can call rewind to the file, and then I have my cursor in this file again at the first position.
Yeah. So, but why would I need this? So we come to another function that is related to this positioning, and afterwards we'll have an example to show you, how to use those functions here. So the third one is the fseek. So this function basically takes the file pointer, an offset, and an origin. We'll have an example on the next slide. It basically changes the current cursor position. So as David mentioned, I could be on position 5 in my file, and then I could go further or backwards a few characters, for example. And I can do this with this fseek function, and origin is the reference point. From where do I want to go back or further a few positions? And I have here a few points that I can use. The first one is the current position. So when I'm at 5th position, I can use seek car. Then I start at this position. I could use seek set, which means it's the start of the file. So I would then seek from the beginning, and seek end would be the case if I want to seek from the end of the file.
Bit confusing,
Yes.
but it's very easy understandable in the next slide when you have an example, I think.
Okay, yeah, hopefully. So here is an example of a file that has a few lines in it with different words in it. In this case, it's names. We have here the position seek set, which is the start of the file. We have the seek end position, which is at the end of this text file. And as you can see here in yellow, we have our cursor, which is our current position. So let's say we have already read from here until here or whatever. So the current position is now at line 8 at the end of the name here.
So when I call ftell like this here on the right hand side, I will get the, in this case, 55th position, because it's the, when I sum up all the characters, it's on position 55.
Yes, so all the previous characters summed up, position 55.
Okay, now I want to change my current position. So what I can do is I'm using fseek, and I hand over the file, and I say, okay, I want to go 7 position, so -7 position.
From where?
From my current, so seek current, which is my currently cursor.
Meaning that we start here and go back 7 characters.
Yeah, so in this case, luckily the name Saruman has 7 characters.
Okay.
So I go to the beginning of this name, and I call fgets to read this name. So when I execute this code here, I can like re-read this name here. After that, after this fgets, my current position is again where the cursor is here because I've read it.
Yes. So it basically sets this file pointer back to at the beginning of this line in this case, because it's 7 characters, and then here we read into the buffer, and when we print the buffer, we have already read again Saruman and have written it into the buffer, and so the current position is again here as at the beginning.
So I don't know how you feel it, but file IO isn't that complicated compared to, let's say, malloc heap or whatever. It's pretty straightforward. Of course, you have to know the functions you can use. You have to know ftell, fseek, fopen, fclose, and so on, fgets. But when you're familiar with that, file IO isn't that big deal, in my opinion. Do you have any questions to file IO in general? Yes. So with this negative value -7, I go now 7 characters to the left. If I say +7 or just 7, I would go to the right. In this case, when I say -7 here, I go in this direction. When I say just 7, I would go in this direction. Okay. If we have seek start and then -7, I think you will. It will work, but again, you are on a memory location you don't own, so you will get the well-ground uninitialized access. Yeah.
So I think there's no need to do this. So I think this could just happen by mistake, right?
Yeah.
So because from the start you wouldn't go back, just go forth.
So again, you're accessing similar if you have an array on the heap. If you're on the 0th element and you go to lower addresses, you're out of your memory addresses.
Are there any further questions to file IO or enums or constants?
So we now have like 15 minutes for one of the coolest topics of all.
I think
my
so,
opinion, because all what we created until now is now combined into a let's say a very, very cool thing we can now use.
Mhm.
And that's data structures.
Yeah. So what's data structures about? First of all, we have to check what is a data structure. So in general, it's a specific way to organize our data. So maybe it's not really a new keyword that we now introduce, like reading from files with or seeking in files, but it's a concept, or data structures are concepts to store data in similar but some kind of different ways, than in specific ways, depending on how we want to further use them and access them. And we've already introduced and used one data structure
very extensively. Who knows it? One data structure.
Any ideas?
Everybody used already.
What this could be?
Whole assignment 2 was about it. Yes.
Yeah. So we will use structs later on, but we wanted to hear a different answer in this case. Yes? Arrays, correct. Yeah. So an array is basically one data structure. So we have in this example here an array of integers, and they are structured in a specific way. So they are one by another, and we can access them with their indexes. Yeah. So,
but these arrays, they have some advantages, of course, because I can go to the next element by just incrementing my memory location. But they have some drawbacks too.
Yes.
And that's why there are different data structures too.
We'll come back to one problem when working with arrays. But now let's have a look into further data structures. So the first we want to introduce today is the linked list. The idea behind it is that we have here different items, so to say, and they are connected or linked to each other. So it's quite similar to before, that we have some items, but in this case we have a first item which is called head, and then this item is linked or has a reference to the next item. And this next item has a reference to the next one, and so on, until the end of our linked list. And then there's no further reference, so we just have, instead of a reference, so an address to the next element, we have a null reference here in the end. Yeah, and this is now a similar but a little bit different way to structure data.
Again, it has some advantages, but also disadvantages. Depending on what we want to store there, linked lists is a better way to use or to organize your data than an array. Yeah. But there are many more.
Sure. So the next one is a stack. A stack is also some kind of list, but it works a bit different than the linked list, because a stack is something like a book stack on a table. So if we put a book on the table, then the book is there. If we put another book on top of the book, we get a book stack, and we put books upon each other. If we want to have a book out of this book stack, then we would have to take the book on top first, and then the second, and then the third. So as you can see here, we always, in this case, have a reference to the top book, and if we want to access books below the top book, we have to pop them down first. So this is for sure a disadvantage if I want to have the book that is placed on the bottom. But if I always want to access the book on top first, then this is a very effective way to structure my list in this case. So this is something like a last in, first out principle.
Just to note here, this does not mean we are not meaning here the memory layout or the memory segment of the
Good point,
stack. This is just the data structure. But of course, the memory segment stack has some similarities with the data structure, because in maybe all cases, the variables are just stored above. Think of a playing card. So if you're playing cards with your friends, if you have a card deck, I don't know all of the card games, but in most of the card games, you will take on top the top card. You will not take out the card somewhere in the middle. You will take out the top card, and if you put it on your card deck, maybe you put it on top and not somewhere in the middle, unless you are doing some magic tricks, maybe.
Yeah, very good example. So imagine that you implement a card game, then you could use this kind of data structure, because you always pop a card from the top, which is exactly what a stack is built for.
Next one, very, very interesting.
Yes.
It's a queue.
And it's kind of the opposite to the stack, right?
Yeah, kind of. So imagine, hopefully, if you want to take the bus and there are a few people who want to enter the bus, hopefully there is a queue and not just random number want to enter the bus. The first one in the queue can enter the bus, and if you want to enter the bus, hopefully you also start entering by adding yourself at the end of the queue. So don't be I don't want to say the word, but don't be don't do that.
Because if you would do that, then it would be some kind of stack, because it would be the last in, first out principle. In this case, for the queue, it's the first in, first out. So first come, first served. As you can see here. And the next and last data structure, within our overview of data structures for today is a tree, which is built
pretty similar to the linked list. So you have a node, or you have an element, and each node has a link to another one, to the next one. But instead of having a link to one, each of these nodes or each of these elements has a link to two other ones.
Or even more. As we can see here, there are references to 3 other items then. And when we work with trees, we also have names for the items and the position of the items. So this item on the very top is called the root of the tree. And then we have siblings for the child nodes of a parent node. So parent node is above the child nodes. And if we just consider a part of a tree, then we call it subtree, and so on. And the last items within such a tree are called the leaf nodes. So this is just the wording that is used when we work with data structures as trees.
Trees, very important for assignment 4. So next week we will talk about trees extensively. And for the assignment 4, just as a hint, you will also work with trees.
And before we will have a look into the problem that we might have, for example, with an array, as we mentioned before, we quickly have a look why there are different data structures, and why do we have to choose which one we would have to use. So the choice of, for example, those that we just mentioned is very crucial for the efficiency. So we as a programmer have to decide which data structure fits best for our use case that we want to implement. As we mentioned, the card game, which is basically then the stack, or the queue if we want to do or implement a queuing system. Because, yeah, depending on the use case, we have different ways of interacting with our data structures, meaning that in some cases we construct our data structure, so for example a list, and then we just read always from the list, or do we often write into the list by modifying the items in it, adding items, removing items? Would be different use cases then, and maybe could be different choices then for the data structure. And also the size of the data plays a role in the choice of the data structure, as well as how often we access and where we access the data. For example, as I mentioned before, if I often want to access the book on the very bottom of my book stack, then a stack would probably not be the best choice, because I would have to first always remove the books on top to get to the bottom book.
But let's say I don't listen to this lecture and I just created an array, because arrays are easy. And now I have the problem that I want to delete one of my, in this case, numbers. In this case, at the index 1, I want to delete this out of my array. So
we have created this array, and now we want to delete an item.
Yeah. So deleting, okay, I could set it to 0.
Yeah,
but that's not really deleting, that's just another value.
Setting to 0 would be an operation that could be easily done.
Yeah.
Could or would be fast, but let's say we do not want to set it to 0, but we would to some kind of remove it, so that we put the further items one position back.
So what I have to do now is I really have to kind of cancel this 4 out, and then I have to shift all of my next items 1 to the left. So
and this could not be done within one operation, right?
Yeah.
So I have to do it manually by first moving the value 8 to position at index 1, right?
Yeah. Then
next step,
12 to position 2, 16 to position 3, and 18 to position 4. And then I also have to delete my last element, because I only have like 5 inside anymore. So 4 inside anymore. So I have to delete the last one.
Yes.
Yeah. That's it. Okay. So that's a lot of operations for just deleting one element. If you use another data structure, for example, the linked list, it will be a lot easier. Yeah, and I think we are now talking, let's use the last 5 minutes for start of the linked lists.
Okay, good idea. So we do not use this exactly same example as we've shown before with those integer values, but we want to imagine to implement a playlist of songs from an arbitrary streaming platform. So in our case, we have a screenshot here from a playlist from a streaming platform with 3 different songs here. And now we want to model this somehow and implement it in C. And we want to use a linked list to link from one song to the next song to the next song and so on. So yeah, the first question is, which attributes does a song have? So we have to somehow think about what is a song. A song has an artist, a title, and a length, for example. So we could represent a song in C code like this. We can use a struct now, where we have an artist, a title, a string, and a length as a short integer. And we call this struct song. Yeah. Now we could, for example, use this Bob Dylan song as one element of this song, or this song struct in this case.
So we created one song, but of course we want to have multiple songs.
Sure.
And when we use a linked list, we need somehow link the first track to the next one and second one to the next one and so on. So how can we do that?
Yeah, so the idea, as you mentioned, is that we have a link from each song to each next song. So from one song to the next song. And a link in this case is just a reference. So we just have to have a reference within each song to the respective next song in the playlist. And how could we implement this to have a reference? We could
use pointers.
Use pointers. Yeah, and what is the next song? The next song is again a struct, right? So it's just again a further such element from this struct. So what we have to have in our struct now is, besides the artist, the length, and the title, is a pointer to a struct song pointer to the next song.
Yeah.
And as you can see here, this could be null. So if there's no further song in the playlist, but if there is a next song, then we would have here the address to this next song.
I want to point out that you cannot write here just song pointer, next song.
Why not?
Because it's not defined here, because it's defined here in the next line. So we have to use this name here because the compiler knows it already. It's above in the code. This is the same as song. So struct underline song underline is the same as the song. Our typedef does that for us. So we have to use this notation.
Yeah.
Another thing I want to point out is it should be a pointer.
Okay. Yeah. So just one remark. So at this point in the code, the typedef is not yet finished because it's finished here. So at this point in the code, there is no song yet, but it's a struct song. So we can use struct song. And why do we use the pointer and not just a struct song here?
Okay, that's a very, very interesting question. We need a pointer here, otherwise it will never work. Any ideas why? Yes. Yeah. So how big is a song? A song has an artist 50 bytes, a title 50 bytes, a length short so 2. So we have 102 bytes, and we have in this case a pointer. A pointer is 8 bytes. Let's say we remove this pointer asterisk here.
How large would it be now?
So it would be, of course, the artist, the title, the length 102 again, but again a song with 102. Which has again a song with 102, which has again a song, and so on and so on. So we will create like an arbitrary big struct, and this, luckily the compiler does not allow.
Yeah.
So you have to create a pointer to the next song and not the element of the next song.
Yeah. So if this element is from the type same struct as we are just defining here, so we have to have a pointer here. Okay, and now we could, for example, add a second song, and as you can see now, the first song has now not null stored in the pointer next song, but it has the address of our created second song. And the second song has as next song null because there is no third song yet. And now we would have, at least in this visualization, a playlist of 2 songs.
Yeah.
And a linked list because now we could start at the first song and go to the next song by accessing this next song pointer. And then we could check whether there is another song by checking the next song pointer again. But we see here it's not, so we know we are at the end of our playlist.
And with that, we can do a lot of cool stuff because we can, of course, print all of it.
Yeah.
We can, of course, add songs, we can remove songs and so on. I think we stop here.
Yes.
And move on to that, or move that content to next week, doing all the interesting stuff with linked lists.
So we'll do some list operations, as David just mentioned, and yeah, continue exactly here.
Okay, then thanks for being here.
Thank you. Have
And
a
see
nice
you next
evening.
week.
See you next week. Bye-bye.